Hello and welcome to a brief overview of advanced sensing and machine learning for wire arc additive manufacturing optimization towards improved quality and energy efficiency. So wire arc additive manufacturing, or WAAM, is a manufacturing technique that deposits metal in layers similar to 3D printing, but uses a technique of welding known as CMT, or cold metal transfer, which is functionally very similar to MIG. So part of this project is we have a robotic arm set up with a welder, and we are performing welds on a carbon steel test plate with a thermal IR camera in front of it. And that thermal camera allows us to capture visuals of the weld. So why are we doing this? We're looking to detect defects in welds. So one of the problems with this process is that it is prone to defects, either because of porosity, fluctuation in energy, uneven cooling. So what we're looking to do in this stage of the process is to identify those defective welds and design a model that can observe the welding process in real time and uh, have vision see the weld process and be able to tell us, hey, something's not right in real time. And this is, tell the robot, hey, something's wrong, do something about it. And I'll pass it off to my colleague who will talk about the CNN AI model and sort of the software side of things.
Hi, I'm Amogh Modgekar Desai, and I'll be presenting the machine learning model we use to classify wells as normal or abnormal based on thermal images. These thermal images are 128 by 128 images, where each pixel represents a temperature value. Basically, they are visual maps of the heat distribution during welding. Our model is a convolutional neural network trained to detect subtle patterns in these images that indicate weld quality. I'll briefly go over each convolutional block and explain what it does. The first convolutional block focuses on fine-grained features like temperature gradients and small spattering. Block 2 starts to analyze localized patterns such as regularities in specific regions of the weld. Block 3 looks at overall heat structure, identifying whether the heat is sharply concentrated or more spread out. Each block has various layers that are listed in the poster. In total, the network has 22 layers, including the output and the input layers. We optimize the model by using a sequential iterative approach, which is also known as greedy search. Finally, our model ended up with an accuracy of 89.3%, and it required a training time of just 4.3 minutes. Overall, our CNN proved effective at capturing both local and global thermal features, leading to strong classification performance in identifying weld quality. Thank you.
And going into the future work is we plan to integrate these features from the model into the actual robotics control system to ensure that the robot can, again, real time see the welding process and be able to hopefully in the future make decisions based on the quality of the weld and take corrective actions to ensure high quality of welding and minimize defects as much as possible. Thank you.